30 minutes tops is plenty. I appreciate you taking time out of your busy day. Is it 9 a.m. there in Sydney right now?
It's approaching 9 a.m. Yep, yep.
Okay, very good. Well, yeah, again, thanks so much for agreeing to do this. John, we've met before. You've joined my class before, but I teach pretty much two classes. One is the debunking course that I teach in the fall, that we kind of cover everything in learning and education that is claimed to be effective but doesn't really have any evidence. And the class I teach in the spring, this one is more the opposite. It's things that do have some pretty good evidence behind them. So thus the inclusion of cognitive load theory, the worked example effect, and so on. And so yeah, just love to chat with you a little bit. And I gave students the opportunity to join tonight, even though I'm just recording this and allowing students who normally have the class tomorrow night to watch the recording. Some of the students chose to join us live because they wanted to meet the John Sweller with a live synchronous meeting like this. So anyway, so John, yeah, great to see you. And I'll start off with congratulations. As you know, I was part of a study a year ago where we looked at the most cited articles in educational psychology journals and the most cited authors from the period 1988 to 2023. And there was, there's only one person that could be number one in terms of the most cited author, and that was John Sweller. Were you surprised by that at all? Were you thinking like, well, of course, who else could it be, right?
Look, I wasn't surprised simply because I could see the trend. It was moving up. It was surprising only in the sense that I've been pushing this. I've been pushing cognitive load theory for literally half a century, and almost nothing happened for most of that time. And then more recently, there was some degree of movement, and then that movement increased and increased and increased. It was exponential, the curve just went up like that. So that's so in that sense, I wasn't surprised, but I was surprised that it happened, and I didn't think it was going to happen during my lifetime. So it's gratifying that it did, and I'd particularly like to thank you for having done the calculations to work that out. So
well, when you don't have much for research opportunities anymore in my career, you end up doing studies like that, right, John? So yeah, that was great. Enjoyed doing that. So you mentioned the trajectory as cognitive load theory is kind of exponentially every year increased with popularity. I also noticed, of course, that maybe 50 years ago, you and a handful of others, tops, or maybe you alone, were doing this type of research, right? And now it's completely different. You have an annual conference on cognitive load theory that's held at international locations. I have attended that twice and hosted it once, and a great group of individuals. But would you say that the number of individuals around the world who do research related to cognitive load theory, has that been a similar trajectory, or has that pretty much been steady over the years in terms of the number who have been involved?
No, it's been absolutely a similar trajectory, and that's what's changed the numbers that you recorded. The number of people who are working on cognitive load theory, I don't know most of them now. Not all that many years ago, I pretty much knew everybody working in cognitive load theory. Not anymore.
Yeah, yeah. Well, it's such a great group. If I have to do comparisons between you and Rich Mayer, I have to say that the cognitive load theory disciples have a much better time at conferences than the Rich Mayer disciples. So they're a more fun group to celebrate with. So John, take us back. You mentioned, about 50 years ago. If you can think back, you're a regular professor of learning, learning sciences, educational psychology. Everybody's doing research kind of on their own thing. Obviously, you're going to be doing something related to learning, but when was it and what was it that sort of cued you to, hey, we've got to come up with sort of a different theoretical model here and think about, this concept of cognitive load and analyzing it and the notion that not all types of load are the same. Some is beneficial, some is harmful. When did that notion come about for you? What take us back to the genesis of that.
Okay, I was running an experiment, or at least I and some of my research students. We were running an experiment, and at that time, my area, I didn't see my area as being learning. I saw my area as being problem solving. Okay, I was running an experiment into problem solving, and we were running a we were using problems that of the following sort. We gave people a start number and gave them a goal number and told them they had to convert the start number into the goal number by either multiplying by 3 or subtracting 27. Okay, they were the only two moves allowed. The start number, got a goal number, and you could take as many moves as you liked to change the start number into the goal number. And people were surprisingly good at that. They didn't have to do the actual calculations. They just had to press a button on a computer and it would multiply by 3 or subtract 27. So all they had to do is work out the sequence. And pretty much everybody that I gave these problems to worked out the sequence. But there was a trick, because the sequence always involved multiplying by 3 and subtracting 27 alternatively. Multiply by 3, subtract 27. Multiply by 3, subtract 27 for whatever number of moves. And some of the problems were just 2 moves, some were anything up to 10 or more moves. And as I said, students didn't have any difficulty solving those problems. But a strange thing seemed to be happening. You couldn't solve the problem anyway. They were chosen so that you could only solve them by alternating those 2 moves. Everybody solved them. And almost nobody at the end of the solution process were aware that they'd alternated moves, that the rule was alternating moves. We obviously hadn't told them you have to alternate moves. That, the problem was to work it out yourself, and they worked it out, but they didn't know they were alternating moves. And I thought, look, this was a toy problem, a puzzle problem. I thought, well, look, we give students problems to solve all the time, especially in subjects like mathematics, but even in humanities subjects where you have to write an essay. If somebody gives you an essay to write, you've got a problem to solve. You've got to work out how to write the essay. We do that all the time, and we often use it as a learning device. But people can successfully learn, or they can successfully solve the problem, but learn almost nothing. And I thought, well, this has obvious educational implications. What's going on here? And the more I thought about it and the more we worked on this, the more I realised that when you're solving a problem, what you're doing is you're looking at, okay, this is where I am now. This is where I've got to get to. You make your move, then you do it again. This is where I am now. This is where I've got to get to. You take much less notice of where you've been and what you've been doing. And the reason you take much less notice is because of the limitations of working memory. Working memory is extremely limited. It's limited in capacity, it's limited in duration. And if you're looking at, okay, here I am, this is where I've got to go, how do I reduce the difference between those two places? You make a move, you reduce the difference. You completely ignore the previous moves you've made. Now, the only way you're going to work out, oh, I'm alternating moves, is when you look back and say, oh, okay, I did this, then I did this, then I did this, then I did this. You can't simultaneously look at where you are now and where you want to go and look backwards at what you've done. Working memory doesn't allow you to do that. It's too restricted in capacity and duration. So I thought, well, if we had simply given people the problem and told them to solve this problem, all you have to do is alternate the two moves. They could have solved any problem, a 100-move problem, easily, effortlessly. And I thought, well, okay, that's a puzzle problem. But the same thing occurs in lots of educational areas. What are you better off doing? Telling people what they ought to be doing, or leaving them to work it out for themselves? And so that led directly to the worked example effect. You can give people a problem. A lot of the initial work was done using mathematics problems, but we've done this on, we've tested this on just about every educational area. You can do this with essays. You get one group of people who you get to solve problems, mathematics problems, or write essay humanities type problems. And you have another group who are given exactly the same problems, but they're attached to a worked example. In other words, you give them the problem and you show them how to solve it. Give them lots and lots and lots of worked examples, more than are normally given. And then at the end, you give everybody a test. And the test is test of problem solving. You give them the problem to solve and you see who does better. And we replicated this experiment on multiple occasions, and it's been replicated around the world. The worked example group invariably does better than the problem solving group. And if you look at the working memory load that's imposed on the worked example group, you find it's less than the working memory load that's imposed on the problem solving group. So the obvious conclusion was, look, when you give people complicated, novel areas that need to be studied, the best way to do that is to give them lots of worked examples to study rather than lots of problems to solve. So that was the first step. But the next step is in some ways more important and massively more complicated. Sorry, was somebody? Oh, I thought somebody wanted to say something. The next step was more complicated. The problems we were dealing with were complicated problems. They were either complicated mathematics problems or they were complicated language-based problems. That worked example effect only works on complex problems. Now, in cognitive load theory, we call that element interactivity, and let me explain that and explain why we don't just call them complex problems. Some things are hard to learn because there's a lot to learn. For example, if you're learning a second language, and let's say you want to learn some of the nouns of that second language, if it's a normal language, that's a very difficult task. But it's not complicated. Element interactivity is low. You can learn the translation of the word cat quite independently of learning the translation of the word dog. I don't need to tell you that learning a second language, nevertheless, is very difficult. But it doesn't impose a heavy working memory load. Other things can be much more complex. Element interactivity can be much higher. If you're writing an essay, as all of you would have to do frequently, I guess, if you're writing an essay, you can't write an essay just by looking at the little bit that you're writing now and ignoring the rest of the essay. You have to keep all of it in mind pretty much simultaneously. That imposes a heavy working memory load. And it's those sorts of activities to which the worked example effect applies. Worked examples are needed on high element interactivity tasks. Same with a mathematics problem. If somebody gives you a simple algebra problem like a plus b all over c equals d, solve for a, make a the subject of the equation, you can't change anything in that equation without considering every single element in the equation. Because if you change one thing, it affects the entire equation. You can't just say, oh, I'm going to make a change here and ignore the rest of the equation. You can't do that. You've got to keep in mind the entire equation, just as you've got to, in one sense or another, keep in mind the entire essay you're writing when you're writing an essay. So that's high element interactivity. One last, second last point about element interactivity. Complexity doesn't just depend on the nature of the material. It depends on what's in your long-term memory. I'll give you an example of that. Let's assume I show you a sentence, the cat sat on the mat, in written form. Okay? In written form, the cat sat on the mat. And I show it to you for 2 or 3 seconds and then take it away and say to you, okay, I've just shown you a whole lot of squiggles, straight lines, curved lines, combinations of straight and curved lines. I've shown that to you for 2 or 3 seconds. Now I want you to copy out or memorize in those 2 or 3 seconds what I've just shown you and repeat it. Now, could you do that? Of course you could. It's a silly, trivial task. It's easy. You could copy out that. You could hold that in working memory and write that out with virtually no errors. How can you do that? Well, the cat sat on the mat for you is a single element. If I'd written out the cat sat on the mat in Chinese and assuming you can't read Chinese, showed it to you for 2 or 3 seconds, taken it away, asked you to repeat what you've just seen, you'd get almost none of it correct. So element interactivity can be changed in 2 ways. You can change the nature of the material, but you can also change it by learning. Once you've learned something, element interactivity decreases. Highly complex information becomes easy, simple, trivial. Now, I don't need to tell anybody here the transformational effects of education. Become educated, we become different people. But that's why we become different people. We can do things, we can think about things which otherwise we couldn't even imagine. I mean, the examples I've given you are trivial examples, but they apply to lots and lots of things that are part of education. So, element interactivity can vary in 2 ways, either by changing what needs to be learned or by leaving what needs to be learned the same, but actually learning it. You can change element interactivity in those 2 ways. What's the relevance of that? Well, the relevance is if you run that worked example experiment that I described before, one group of people shown a worked example, another group of people given a problem to solve, and the people who are shown the worked example do better. In education, as you get better and better at whatever it is that you're learning, element interactivity decreases. As element interactivity decreases, the difference between and the advantage of worked examples over solving problems also decreases. Increase expertise more, and there's more of a decrease. Eventually, you don't get a difference between worked examples and problem-solving groups running a randomized controlled trial. But it gets worse. As expertise increases further, you again get a difference, but in the reverse direction. People given worked examples to study at that point do worse than people who generate problem solutions themselves. So what's going on there? Well, firstly, it's called the expertise reversal effect. As expertise increases, a lot of the cognitive load theory effects reverse in direction. And the question is, why and what's happening? Well, what's happening is that when you run a worked example experiment, compare worked examples with problem solving, if you do that with low element interactivity information, problem solving is better. Worked examples are better when element interactivity is high. In other words, when the problem is a very difficult problem for you. Put that in a normal educational context and you can get some sort of an understanding of why that happens. Let's assume you're learning something that's very complex and you've got to keep going over it again and again, and that means you ought to be studying lots and lots of worked examples. Does that mean that's all you have to do? No, of course not. You know perfectly well that once you start to learn more and more of it, you don't need to study worked examples anymore. What you now need to do is start practicing it yourself. If all you do is study worked examples, yeah, you'll improve a long way. But we all know perfectly well, you've got to practice it as well. And the reason for that is as your expertise increases, you need to practice actually solving the problem. Now, in mathematics, sure, you need to study lots of worked examples, but at some point, you need to practice solving the problems, and you'll keep getting better as you solve those problems yourself. Studying essays, and this is not often done in most educational contexts, but ideally, you should start by studying lots and lots of essays, but you can't stop there. At some point, you have to start writing essays yourself. The reason this effect is called the expertise reversal effect is because you get that reversal. But there's another effect functioning here, and that's called the redundancy effect. Studying worked examples is extremely useful when you're a complete novice in an area. Becomes less and less useful as your expertise increases, because studying worked examples reaches the point where you can't you need you need to actually work through the problem yourself at some point. Working through the problem yourself early in the piece imposes an excessive cognitive load. Studying a problem decreases that load. Studying a problem when you've reached a certain level of expertise is redundant. You don't need to study them anymore. You need to practice it yourself. So they're three of the closely interconnected cognitive load effects: the worked example effect, the expertise reversal effect, and the redundancy effect, which leads to the expertise reversal effect. As I said, this can be quite complex. Element interactivity is high. Hopefully what I've been saying has some degree of intelligibility. There's a lot of literature out there on that, and it may be, it's the sort of thing which in many ways it's better to read than to listen to, but I hope I've managed to put it together in a way that's sufficiently intelligible to be of some use to you.
John, that was fantastic. Really appreciate that. Just one more question tonight. I don't want to go much past your time, but you did a good job laying out kind of the rationale behind cognitive load theory and the reason why you have to provide support, scaffolding, if you will, but more importantly, as you know, worked examples are going beyond scaffolding in the sense of showing people the steps and the rationale and so on. But the flip side of that, as you and I have discussed, another approach to helping people learn or solve problems is this generation effect, or what some cognitive psychology researchers have termed desirable difficulties. And it's funny because to me, those are sort of symmetrical somewhat in the sense that cognitive load theory typically approaches a problem that has high element interactivity and the learner is a novice. And by providing some supports and getting rid of extraneous cognitive load, you facilitate problem solving, you facilitate learning. But with desirable difficulties, it's the opposite. It's kind of like what you're saying. If you're an expert and they keep giving you examples over and over, it actually is counterproductive. And with desirable difficulties of the generation effect, there's an attempt to make things more difficult. It's an oversimplified way of saying it. But you've gotten into that recently. Many of your studies have taken on things like spacing effect and retrieval practice and things like that. Tell me kind of why you got into that area and sort of stretch the boundaries of cognitive load theory research to sort of incorporate sort of this flip side of an approach to instruction.
Yeah, the summary you just gave is great. When you look at when you look at let me begin with desirable difficulties. You only want to bring in desirable difficulties, the so-called desirable difficulties, when you're dealing with low element interactivity information. That's why you get the expertise reversal effect. Uh, Solving problems becomes desirable when it's low element interactivity. If you give somebody something which, and all of us will have come across this ourselves, you're looking at something, you know, whoa, this is difficult. I'm really having difficulty understanding this. The last thing you need is a additional difficulty of any sort. You do not want a desirable difficulty. There's no such thing as a desirable difficulty. The stuff is sufficiently difficult without changing it in any way. But if you're given stuff which is difficult because there's a lot of elements, but they don't interact, learning the nouns of a second language, learning the symbols of the chemistry periodic table, all those sorts of things. These can be very difficult tasks, but they're low in element interactivity, and using the generation process, that's fine for those. Never ever try to use the generation process on something that is high in element interactivity. It's catastrophic. It just doesn't work. Um, um, yeah, the spacing effect, interleaving effect. Let me go back to the spacing effect. That's a really interesting effect because it's the original effect which started off experimental psychology back in the 1800s. It's a very, very old effect. It almost certainly has multiple causes. The spacing effect occurs when you compare again using a randomized controlled trial, give one group of people a whole lot of material to learn without spaces between them. Give another group of people exactly the same material, but space it over a longer period. And you find that the people who've been given the material spaced over a longer period with gaps in between do better than the people who had to learn it in a massed form. So it's massed versus spacing. And it occurred to a few of us that spacing effect may be due, at least under some circumstances, almost certainly not under all circumstances, but under some circumstances, because working memory, once it's been used, which is another way of saying, once you've been, working very hard on something, thinking really hard, working memory capacity may well decrease. It's really a technical way of saying you got tired. And, we get tired when we do a lot of work and we have a rest. What happens during rest? Well, working memory capacity decreases as we keep working and recovers during rest. And we've done experiments demonstrating that's exactly what happens. So if you've been doing a lot of work, you may want to seriously consider going away and having a rest. Don't keep pushing yourself. You may find you learn much better by having relatively frequent rests to recover, go away and do something else which doesn't involve a heavy working memory load. If you're doing something that involves a heavy working memory load, working memory capacity deteriorates, resources deteriorate, and recover with rest. So we certainly didn't invent the spacing effect, but it's a very well-known effect, and it may well be, at least under some circumstances, a cognitive load theory effect. In other words, we can explain it in terms of changing cognitive load depending on how rested you are. And of course, the best rest of all is to get a good night's sleep, but that's another issue.
Well, John, thank you so much. I'm not going to press my luck. I could talk to you for 3 hours straight, and I really do miss that. You're gonna have to tell me when Cognitive Load Conference comes to the States again, and I'm gonna do my best to make it just so I can catch up with you. But the last thing I was gonna say, looking at your productivity over the years, you've been emeritus now at University of New South Wales for a while, yet your productivity still exceeds most of the young, energetic professors that are out there. And please don't ever stop. Don't ever be seduced by retirement and stop, because we need you in the field. We need your voice, and keep doing great things. Like I said, you've been a good mentor to me, colleague, friend over the years, and really enjoyed seeing the stuff that you do and the stuff that you've contributed get more of the recognition and visibility that it deserves, especially in the last 10, 20 years, I think, that I've witnessed. So please continue to do what you're doing.
That's very, very kind of you. Thank you. And look, you've done more than most people in getting cognitive load moving. The really, really, really important publications for cognitive load came out in Educational Psych Review when you were the editor, and can't thank you enough for that. So thanks again, and it's been really great talking to you. I enjoyed the time.
John, in the interest of time, I'm going to ask the students if they have any questions to send them to me, and I'll send them to you in an email where you can respond a little bit more thoughtfully on your own. But I'll definitely do that and follow up. But I want to be respectful of your time tonight and this morning for you. And yeah, thank you so much again. Great to see you, and hope to see you sometime soon.
Thank you for inviting me. It's been a pleasure meeting up.
Take care.
Okay.
Bye, everyone.
Okay.
Thank
Bye.
you.